Welcome to Key Curriculum Press's webinar today on geometric functions. Today's presenter is Scott Steketee, and without further ado, I'm going to transfer his presentership to him. Okay, Scott, I can see your screen.
Excellent. Please let Andres or Elizabeth know in the chat panel if you encounter any difficulty seeing my screen or hearing me. And I'm delighted to be presenting this webinar today. I've been working on geometric functions for a while now, and I'm very excited about the possibilities of using geometry as a way to provide students with better experiences, more visual, dynamic experiences with functions than they've had in the past. So I have a title screen here that has some that's created using a very simple function that we'll come back to at the end of the presentation. Let's begin though with a quick review for people who joined us late. I'm Scott, and I'm presenting the webinar. And Elizabeth and Andres will be answering questions for you. And the central problem that I think geometric functions really helps us with is the fact that students find variables and functions so hard to understand. And there are a number of reasons for that. Variables really are used in many different ways. For instance, one of the most common ways of using variables is equations like 2x equals 6, but the x there is not really a variable. It's simply an unknown number. And there's a fair amount of literature that, that suggests 4, 5, 6, 8 different distinct uses of variables. And students have to put all those different uses together into one concept, and that's hard. It's particularly hard because they don't get much direct experience with variation. So actually varying a number is not something that, that students often have a chance to do, even with graphing calculators, for instance. They don't do much with actually varying the numbers. And we want to provide more direct experience with variation. Similar to variables, functions, an awfully complex and abstract concept. There are a couple of different ways of thinking about functions. And much of the thinking that students do about functions doesn't really pay attention to function behavior. But that's at the very essence of what a function is and of understanding functions. So we want to introduce function behavior in a more concrete and more compelling way than students often view it. So one piece of that is giving students a chance to experience functions more dynamically. And another piece is providing representations that are more compelling than the ones that they're used to. So just a quick summary here. Variables are hard to vary. Function behavior is missing. Transformations in functions don't end up being related in students' understanding. Students think of transformations as being geometric objects, functions as being algebraic objects, and they don't even see the connection. Whereas if you look up in a mathematics dictionary these two words, transformation and function, you actually see that they are synonyms for each other. But we don't talk about transformations as functions. So one of the most important things we're going to do today is to use transformations as examples of functions that give students the ability to vary functions, to vary variables dynamically, and to observe the behavior of the resulting functions. I'll just mention that Cartesian graphs are powerful, but they're very limited, and the dynamic nature of functions doesn't actually come through in Cartesian graphs, at least in the way that most students end up seeing them and using them. I want to mention one other thing, which is that the Common Core standards place a big emphasis now on transformations. Starting in 8th grade and on through high school mathematics, transformations get a lot more emphasis than they have in many curricula in the past. And it presents a tremendous opportunity for us to use the new emphasis on transformations as a way of also making functions easier for kids to understand. So, in today's webinar, we're going to do a number of things. I'll just skip through this very quickly, but we're going to vary some variables. We're going to pay attention to function behavior. We're going to use a geometric approach to develop the ideas of domain and range so that students have a visual representation of what domain and range are. We're going to introduce function notation in a way that fits very nicely with the geometric creation and observation and exploration of functions. We will dance the geometric function dance. We will compose geometric functions and have a way of looking at composition of functions and relating the composed function to the notation that we use for composition. And we'll end up by creating striking visual effects like the one on the title page. So let's begin. We need to begin by introducing the idea of function itself. I like to do this. I like to introduce the idea of function in a geometric way by actually having students vary the variables. So on this page, we have a number of variables. The variables here are points because the functions that we're looking at are transformations of these points, and we have to find out who is related to whom. So let's drag point A. That's our independent variable, and we can see as I drag point A that only one of the other points moves with it. So we can infer that dragging variable A causes Y to vary as well. Let's see what happens if we try to vary Y. So I select Y, I try to drag it. Oh, it's not going anywhere. So Y cannot control A, but A does determine the position of Y. So we have an independent variable that we can move anywhere we like, and a dependent variable whose location depends on the location of the independent variable, but which cannot be moved by itself. So let's experiment with some more of these variables. By the way, in this particular activity, and all the activities that I'm going to show today, all of these activities are available through the URL that I'm going to show you at the end of the webinar. And they all contain both sketches and worksheets that give all the instructions for how to use them. I'm showing, by the way, only the first page of the activity on identifying functions. And I'll tell you a little bit about what the other pages look like in a moment. But let's get back to experimenting with our variables here. Oh my, variable B cannot be moved. That means it must be a dependent variable controlled by something else. Well, maybe we'll find out about that later. Variable C, okay, that one moves, and it controls dependent variable D. Again, if we try to drag the dependent variable, it goes nowhere. We have to control the independent variable to move the dependent variable in some way. Experiment with some more. Point V, well, that one's an independent variable, but it doesn't seem like it has any dependent variables that depend upon it. How about point E? Another dependent variable. It won't go anywhere. Point Z. That's the one that controls point B. So independent variable, dependent variable. All right, let's try point W. Oh my, that controls two dependent variables. And finally, points X, E, and Y are all dependent variables that can't be moved independently. The remaining pages of this activity have a number of situations in which you have two different examples. For instance, you might have this example with W, X, and E, and you might have this example with A and Y, and the directions on each of these pages are W controls a function, W does not control a function, A does, and the progression through these pages leads students to develop their own definition that a function consists of an independent variable, a dependent variable that depends upon it. There must be exactly one dependent variable, not 2 or 3 or 4, not 0, but 1. So students in this way have a chance to develop their own definition of the function and do it in a way that where they have nice visual representations and dragging the variables and watching the behavior of the function. The next activity I want to show a bit of is this activity on which function does not belong. So 3 of these functions are from the same family, but one is different. I'm going to drag each of the independent variables. And you notice, by the way, that now we already have cues both in the color and in the notation to say that function f relates point A as the independent variable to f of A as the dependent variable. So I'm going to drag each of these, and your job is to tell me which one is different from the others. 3 of them are in the same family, and 1 of them is in a different family. And I'd love to have somebody, I'd love to have folks in the chat panel tell me which one is different from the others. Which function is a different family from the other 3? I'm not seeing any answers in the chat panel just yet. Hopefully we'll have some responses soon. Okay, we've got a couple of different responses. C and H of C, B being different. And these are actually quite a bit of fun for students to play with. If I turn tracing on, by the way, I can see when I drag D or when I drag C, I can see what the pattern is, and these traces might help to make your decision. Another thing that can come out of this discussion, once students have determined, for instance, that you can bring A and F of A together at a number of different positions on the screen. Similarly, C and H of C can be brought together at a number of different positions. D and J of D can be brought together at a number of different positions. But B and G of B only have one place where they can be brought together. That's the sort of behavior that we want students to be thinking about for functions. When we translate that behavior to the numeric realm, it's very, very useful for students to be concentrating on the behavior just in the same way that they're looking at the behavior in the geometric realm here. Okay, one other piece that's going to come out of the discussion about this is how we name the functions. So some students might want to say, well, B is the one that's different. But in fact, A and B and C and D are all independent variables. But the function itself, we're going to call G. So in this activity, we have a chance to introduce the idea of function notation, and that we use G as a shorthand to represent the behavior of this function and how it's different from the behavior of functions f and h and j. Okay, so that's families of functions, and we've also introduced the idea of notation here, of function notation. Let's go on. The next activity that I like to have students do is one in which I have them use geometric transformations to create their own functions. So in this activity, they start from a blank sketch and create a function. All right, so let's do that. Let's create a function, and I want to make this, let's say, a reflection function. The geometric function activities can include 4 different versions of this activity, 4 different worksheets, one for each of the families for reflection, dilation, rotation, and translation. But since I'm going to create a reflection, I'm going to begin with a mirror, and I'm cheating a bit. You might be happier if I do a full line, although Sketchpad can reflect across. Let's cut that. Sketchpad can reflect across segments as well as full lines, but let's make it a full line just for the sake of being mathematically accurate here. So that's my mirror. I'm going to create an independent variable, and from the transform menu, I'll choose reflect. There's only one line in my sketch, so Sketchpad automatically marks it. I hope you saw the little animation on the line. Sketchpad automatically marks it and creates the dependent variable. So now I have an independent variable and a dependent variable. And part of this activity is carrying forward the idea of the function notation that we've already seen in the last activity. So as part of that activity, we're going to identify this mirror as line J. We're going to identify the independent variable as point X. And students will then identify the dependent variable, not as x prime as we normally use in transformations, but as a function which is the reflection about mirror J of point X. So I'll click OK, and we've now used function notation to say this is a reflection about mirror J of point X, and students will also trace those points, so through the traces they can get a good sense of the behavior of the function, and they can observe that the places where a reflection comes together are in fact at the mirror. They can also experiment with domain and range. Let me turn off the tracing for the moment on my independent variable and erase the traces. And as part of their investigation, students will take the independent variable and attach it to a polygon in order to see when the independent variable moves around the border of the polygon, what shape do we end up with for the dependent variable. So this is part of investigating the behavior of the function. With the polygon and point X selected, I'll choose merge point to quadrilateral, and then begin dragging the independent variable, and the independent variable is now restricted to this polygon. In other words, we have a restricted domain. And if I like, I can take the independent variable and create an action button that animates the independent variable around quadrilateral number 1 at medium speed. I can make it go faster or slower if I care to change the button. And by clicking the button, we get to see a very regular motion of the independent variable, and we get to see what happens to the dependent variable. We also get to see, if we like, what would happen if the shape of our domain, if we used a different domain than we started with here. So let me change the domain a bit. And let me actually, in this case, let's say, move the domain in such a way that it crosses the mirror. Erase the old traces and animate again, so that we get to see how this restricted domain translates into a corresponding range for the dependent variable. So there's a lot for students to see here about the behavior of functions, about how we use function notation, and also to have a visual representation of the domain and the range when you restrict the domain. It's very hard for kids to understand in the numeric realm why we restrict domains in the first place, but if they have this as a starting place where it was useful in looking at the behavior of the function to restrict the domain just for our own purposes, then restricted domain in the numeric realm is going to make more sense to them.
Okay, Scott,
so I'd like to pause for a moment for questions.
Perfect timing. So, yeah, the comment about people love the connection to the Common Core, which is true. I myself noticed a big emphasis on transformational geometry as really the beginning point of the high school geometry framework. But the question came up, in this reflection, if you don't label it, wouldn't you be able to drag either point? In other words, how do you identify what's the independent variable? Wouldn't both points be draggable in a reflection?
That is correct, because Sketchpad is sophisticated enough to recognize that this function is invertible. The inverse function actually is a function, and because it's an invertible function, Sketchpad actually provides you with the capability of dragging the dependent variable. But what's actually happening here is that Sketchpad has been smart enough to recognize the invertible nature of this function so that we can use the inverse function. That's really what I'm dragging right now. So in the prepared sketches, to avoid that confusion, I actually use the properties dialog box for the dependent variable. So I'll select it, choose properties, and I will make the dependent variable not arrow selectable so that students don't get confused on a prepared sketch by being able to drag the dependent variable. I don't want Sketchpad's sophisticated capability of inverting a function to confuse students until we get to the point of teaching about function inverses later on. I hope that helps to explain things. Students will notice when they construct the function themselves, as I did here, they will certainly notice that they can drag the dependent variable as well. But at least in that situation, there's no confusion because they know which point they created and which point was the dependent variable because they created it using the transform menu.
Margaret mentioned that there's also a way to introduce inverse functions. And Raylan would like to know if you could quickly show again how you animated the sketch, how you created the action button.
Sure. First of all, I didn't create the action button until after I had merged point X to its restricted domain, because otherwise we wouldn't have known where to move point X. That done, once it's been merged to its domain, I can select point X and from the Edit menu, choose Action Buttons and Animation, and I get to move point X. I will get a button that moves point X forward around the quadrilateral at medium speed. I can make it move backward instead of forward. I can make it move one time only, let's say fast. So now I've got a second animation button that goes one time only, the other direction, fast. If I erase my traces so that we get to see the actual behavior here, animate the point, it goes much faster. And in fact, we can even see the increased speed because the individual dots that result from the tracing are slightly separated here, where when we vary X more slowly with the first button, the dots are so close together we can't distinguish individual dots. So we can actually use the traces to evaluate the speed with which the two variables move. And we'll see how that comes in looking at behavior functions in just a second. Anything else?
No, great. You're getting close to the halfway point. But...
Oh, okay. I think we're doing all right. We'll see. So I want to do one more of these, create another function. And this is going to be a dilation function, so I'll need a center point. And this time I'm going to go to the transform menu and mark that as my center point. I could have done the same thing to mark a mirror for the reflection one, but I had only one possible mirror, so I didn't worry about that. So I'll mark that as the center. It gets a quick animation. And now let me create an independent variable. And I sometimes use keyboard shortcuts. A keyboard shortcut to label a point is Command/ or Control/ in Windows. I may actually take advantage of those shortcuts at some times during the presentation, but everything I do by keyboard is available from menus. So I'm going to call this X again because I'm hung up on X at the moment, or students are actually hung up on X as the independent variable. We're going to want to give them plenty of experience with other independent variables than X, but I'm just going to stick with X for the moment to emphasize the connection with what students are so used to seeing in the numeric realm. Okay, so that's my independent variable X. I'm going to transform that by dilating it, and scale factor of 1/2. Let me use a scale factor of 2/1 instead. And using my keyboard shortcut here, I'm going to call this the dilation about point C, and I haven't labeled point C yet, but I will in a moment, by a factor of 2 of point X. And to make sure that I'm not lying, I better label this point and call it C. So now we have the dilation about C by a factor of 2 of point X. And if we turn on tracing for these 2 points, we'll get to see what happens when we drag the independent variable. And we see that there is only one place where we can drag the two together. We'll even give this a name. We'll call that a fixed point, because the presence of fixed points and the number of fixed points and their configuration is one of the things that distinguishes function families from each other. We'll also notice that in the trace, the points corresponding to the dependent variable are twice as far apart as the points, as the dots from the independent variable. And we notice that as we move things, that the dependent variable is moving twice as fast as the independent variable. So we get to talk about relative rate of change, relative speed of the two variables, and that's an important part of the behavior of functions. How fast does the dependent variable change compared to the independent variable? Students often have trouble with the concept of slope because and relating that to rate of change, because slope is a characteristic of a Cartesian graph, and they don't quite see how that relates to the rate of change of the variables. But if we get them to spend more time thinking about the rate of change, the speed with which the variables move, then we can get that idea of relative rate of change embedded in students' minds much more easily. So that's a second example. And I wanted to bring this one up because this is the first one where we see different rate of change between the independent and dependent variables. Okay. If there aren't any questions right now, I'll jump to the function dance activity.
Just a quick question came up. Just the traces are not selectable, right? Was the question?
No. No, you can't select the traces, and in fact, the traces have gone away just by going to a different page. Traces are very ephemeral. We can, however, this is an interesting question, and let me address it for a second here, because if I restrict the domain, unlike a trace where I've dragged point X in a free-form way, by restricting point X to a domain, from the edit menu, merge point to quadrilateral, so now X is restricted to a domain. The domain here is well defined, so besides being able to trace to see the range, with a well-defined domain like this, it's actually possible to select the independent and dependent variables and tell Sketchpad to construct the locus. So I've just constructed the range using the locus construction. And if I were to turn off the tracing for those two objects and erase my traces, I now get to see how the range changes. Oh, it looks like I had the locus selected. I'm sorry. I've left the tracing on for both variables and for the locus as well. Let me fix that. I'm going to turn them off for all of those. Again, erase the traces. And now we can see how the range changes as I change the domain, the restricted domain for my variable. So that's another interesting way of using the geometric approach to be able to dynamically change the restricted domain and watch its effect on the range. Okay, shall I go on?
Yes, you should. Thanks.
Okay. So function dance. I had a great time doing this with a couple of groups of kids in late June. The function dance activity, also downloadable at the end. I give you the URL and everything. The function dance activity we actually began by taking the class into the hallway and selecting one student to be the independent variable, another student to be the dependent variable, and we had a couple of choreographers whose job was to help those students dance a particular dance, and we danced translations by various vectors. We danced rotations by various angles about different center points. One of the choreographers had to stand in a certain spot to be the center point for the rotation as the independent and dependent variables tried to match up their motions. And then we went back, after we did this for a while, we went back to the classroom and did it on the computer. So here we're going to do it on the computer. The hard part of the activity is being the dependent variable. The dependent variable has a very difficult job. Point P is not in the correct position to be the dependent variable for point A on its restricted domain translated by the vector j. So to begin, we have to find the correct place now for the dependent variable using the vector j related to the independent variable a. So now I've moved p so it's in the correct place for the dependent variable. You note that I called this p. I did not call this the translation of a, because in fact we can vary p. P is actually independent, but we're going to try to act as though we're the dependent variable. So when I click ready, set, go, the countdown will begin. I have 3 seconds to get ready to drag point P to try to act as though I'm the dependent variable for this function. And I'm not all that great with the trackpad, but here we go. Oh dear. I have more trouble at the corners than anywhere else. And sometimes I even get ahead of myself. Oh my goodness. Okay, there we go. So this can be surprisingly challenging to actually try to be the dependent variable. But what a nice way for students to experience function behavior, to try to act as though they're the dependent variable for a function that they know. So let's check the result. If I check the result, we get to see how I did, and I'm pretty shaky here going around, but I did generally succeed in following the range that corresponds to this restricted domain. Here's another example of a function dance. This one is a rotation by 180 degrees, and you can see already how much more challenging this is going to be, trying to get point E in the correct place to be the dependent variable for independent variable D rotated by 180 degrees. Let me try ready, set, go, and see what happens. Oh dear, oh dear. So this is quite challenging. And in fact, I'm going to give it up right now, but I might like to try this again a bit later with the speed turned down to give me more time to figure out where I should be going. In fact, if we turn the speed way down, you'll see that I actually have a bit of a better chance of following point D. Not much better yet. So this is a really fun activity for kids and very challenging, and also emphasizes the behavior of the function, the relative speed of the two variables, and the relative direction of the two variables. Now, with numeric functions, you don't get questions of the relative speed of x and f of x. I'm sorry, you don't get questions of the relative direction of x and f of x, though you might have one that's increasing when x increases, f of x decreases. That's an important distinction about direction that we do want to make with students, whether the slope at the moment is negative or positive. But the whole connection with the relative speed of x compared to the speed of f of x is the concept that we want students to understand about how the dependent variable relates to the independent variable. So that's a lot of fun, and kids love that. All right, composition of functions. Boy, what a hard topic for kids to understand. And one of the things that's really hard for them to understand, apart from the idea of composition itself, is they really have trouble, in my experience, with the notation for composition of functions. They get completely mixed up about f of g of x versus g of f of x and so forth. So I'd love kids to actually create that notation themselves by taking two functions and composing them and using that process of creating their own composition in the geometric realm to investigate, to develop the notation, and also to investigate the question of, is f of g of x the same as g of f of x? And they can do all that pretty easily with geometric functions. I'm going to take a quick shortcut here. My shortcut is going to involve taking my reflection example and splitting the independent variable from the restricted domain. I'll get the restricted domain out of my way, and I'm going to copy this. So copy and paste into my composition page. Oh, I tricked myself here because, as you might remember, I made the dependent variable unselectable. So I'm going to have to hold the control key down to get the context menu, to go to properties, to change this to be arrow selectable again, and now I can copy and paste into the composition page. So this is my first function, and I just did this right now to save some time during this presentation by using the two functions I created earlier rather than by creating some new ones. So here's the dilation. I'm going to split point x from the quadrilateral, move my, oops. Oh, okay, I don't need the locus. So here I have the independent variable, the dependent variable, and I need to bring my center point with me. So that's what I'll copy. Paste that into my new page. And let me do one more thing, which is to eliminate the possible confusion here of two different variables called x. So this one's going to be called y. I'll get this one named appropriately. And I see that I've lost the correct label for my line when I did my paste. So now I have two functions, x and the reflection of x across line j, independent variable y, and the dilation of y by a factor of 2 about center point C. So now I have two functions on the same page. If everybody's ready to go, we will look at now at the composition of these two functions. First, in this activity, I have students play around a little bit, erasing the traces and doing something like dragging point x to create a trace. Oh, I should have point x traced as well. Let me start that drag again. So I just used keyboard shortcuts to trace x and its dependent variable. And in order to see what happens if we first reflect and then dilate, I'm going to need to put point y at the starting place for where I dragged, for where the dependent variable of the first function went. Because I want y to follow that same path as the dependent variable so I can see when this was reflected to here, where did point y go? I'm not explaining this very well. The worksheet actually does a much better job of explaining this, this process. So let me trace both of these, trace the points, and I'm going to color those points differently so that we have a different set of colors here. And if point y were to follow the path of the dependent variable of the first function, I can see what shape I get by taking point x, reflecting about mirror j, and then dilating the result about point c by a factor of 2. Now, I want to move in the direction of having this happen automatically instead of just having to do a drag. And by the way, if you have Sketchpad Explorer on the iPad, a beautiful thing about the iPad version of Sketchpad is that it's multi-touch. So I could have had one student dragging point X and another student trying to drag point Y at the same time to match the position of the dependent variable. I can't do that on the desktop, but on the iPad Sketchpad Explorer, it works beautifully. To make this happen automatically, I'll just merge these 2 points. I'll merge independent variable y, the green one here, to the dependent variable for function reflect across j. So with those 2 selected, I'll merge those points, and now variable y, we no longer have an independent variable y. In its stead, we have r sub j of x. So with variable y gone away, I actually need to change the notation here, because what used to be variable y is now r about mirror j of x. So I've just put the label of what used to be the independent variable for the second function into the label for the result, and I now have the dilation about c by a factor of 2 of the reflection about j of x. So all this makes sense. I'm going to erase the traces, drag point x some more, and we can see what the composition of these 2 functions looks like. And if we like, we can, as we've done before, create a restricted domain to give us a better sense of what's happening here. And this is where the restricted domain actually begins to get really valuable.
Scott, can I stop you right there? We had a question earlier. Can you, just that merging a point to an object, can you explain that again?
Sure. Let me go back to that in just. Let me go back to that in just 1 second.
Thanks.
Because I don't want to. I'm so close to the point of being able to see through the restricted domain the range of the first function serving as the domain of the second function, and the range of the second function showing the result of the composition. And I just wanted to leave that happening while I talk now about merging the independent variable of one function to the dependent variable of another.
No, actually, more generally, yeah, that's fine too. But even just merging a point to a polygon.
Sure. I've used that in several instances. So
right. I just wanted
let me just off on the side. Take a new point. Take a polygon. I'll also put a circle over here just for the heck of it, and a segment maybe. And the ability to merge and split gives students wonderful opportunities to do what if explorations. So I can select this point and the polygon and merge the point to the triangle. That's what I did before. I'm going to skip that right now, and I'm instead going to select the point in a circle and merge the point to the circle. And now my point is stuck on the circle. No matter where I drag it, it won't leave the circle. If I decide later that I want to see the result of whatever construction this results from this, I want to play the what if of what if this was attached to a segment instead of a circle. To play that what if game, I can split the point from the circle, select the segment, and merge the point to the segment. So it allows for an enormous amount of what-if experimentation. And in this example, it allows us for the what-if experimentation of what if the independent variable of the dilation was merged to the dependent variable of the reflection. So it's a natural way to actually compose two functions by using the merge command. So I hope that helps.
That was great. Thank you.
Okay, I've got just enough time to show you how we did the swirl. Oh, blank sketch again. Do we have time? Oh my goodness, 9 minutes. The answer is yes, we have time. Start with the center point and label it C as the center. And the swirl is based on a rotation of sorts. So here's my independent variable. Let me call that X. And I'm going to rotate that independent variable, but I'm going to rotate it in a curious way, because I'm going to base its rotation on how far away it is from the center point. So I'm going to measure the distance between point X and center point C. And I've made the mistake of leaving my preferences to show distances in pixels. Normally they show up in centimeters, so I'm going to make them centimeters here and make that slightly larger. Okay, so this is 3.66 centimeters away from point C, and I'm going to use this distance to calculate an angle by which to rotate. So from the number menu, calculate. I'll start with the distance, 3.66, and I'll multiply that, let's say, by, how about if we use 10 degrees per centimeter. Let's see, 10 degrees, that gives us, I want to do 36 degrees, but this says centimeters degrees, so I'm going to need to divide by 1 centimeter just to get my units straight, so that my units are in degrees, because I have to have degrees if I'm doing a rotation. Okay, I hope that calculation makes sense. I've taken the distance, multiplied by 10 degrees, divided by 1 centimeter so that my units are correct. So now I've got approximately 37-degree rotation. I'm going to mark point C as my center point. I will rotate X by, not 90 degrees, but by this calculated angle value. And I want to name this, so I'm going to name it not X prime, but the rotation about point C by an angle that I'm going to call theta. And when I do the curly brackets around the word theta, T-H-E-T-A, Sketchpad is smart enough to change that into the symbol for theta of X. So there's my rotation. And now I get to see, if I drag farther away, the rotation becomes more. If I'm closer, the rotation becomes less. And I get to see now, if I were to, well, actually I have one more step I want to take here before I go getting a picture, which is to observe that Sketchpad gives you the capability, when you select the independent and dependent variables of a function, of making that into a new transformation. In other words, a new function that Sketchpad knows about that takes x to the rotation about c by theta of x. So we now have a new item on the transform menu for the transformation that we've just created. And I can actually use that to transform, let's say, a circle. If I wanted to see what a circle looked like when that transformation is applied to it, I get to see. And in fact, you'll note that if I drag point X around, if I made this my restricted domain, you can see how the rotated image using my new function actually traces out this range. Okay, but I'm not going to do that with a circle right now. I'll get rid of my circle because I want to do it with a picture. So I'm going to go to Sketchpad's picture gallery. I'll select this category of pictures and copy this image, return to Sketchpad, and paste my picture. So I now put my picture right here. I like to put the vanishing point of the road at the center point of my rotation just because it's a nice way to do it. Select the picture and apply this transformation. That's where the swirl image that you saw earlier comes from. And if we change the calculation here, we get to see, let's say instead of 10 degrees, I make it 20 degrees. We'll see how much doubling the swirl does. And the image on the title page actually had this as an animated value, which was how you saw this, the image swirling and unswirling. Okay, so 3 minutes left. I'm going to show you the resources. I'm going to say one more thing real quickly. When you download this sketch, I have 4 pages here on my thoughts about when these activities might best be used. In units on geometric transformations, either in middle school or high school, and so forth and so on for the introductory activities. I have some comments on using dynagraphs, which are a wonderful way of making the transition from a geometric approach to a numeric approach. I have usage suggestions for the second group of activities, which includes composition and inverses and so forth, and the third group of activities, which are functions as mappings, like the mapping that we did with the swirl. So we've done an awful lot today. We've dragged variables and emphasized function behavior. We've looked at different families of functions according to their behaviors. We've restricted domains. We've used function notation. We've applied functions to whole sets of points, like the picture of the road. We've done compositions and so forth. All the resources are available here. The zip file for the webinar will be, you will get that within the next few days. The recording will be up on the website. All of the activities are at this URL right here, kcptech.com/dynamic_number/geometric_functions.html. So that's where you'll find the worksheets, the sketches, and everything else that, and for many of the activities, teacher notes as well. I don't have teacher notes finished for all of them, but for many of them I do. And finally, Sketchpad Lesson Link contains all the dynagraph activities and a whole bunch of other useful algebra and geometry activities, over 500 total. The help menu also has some sample sketches. And I'm sorry, actually I meant to say teaching with Sketchpad has sample activities as well, including one of the dynagraph activities. So samples of the Sketchpad Lesson Link activities are here under Teaching with Sketchpad. I'm sorry, I left only 1 minute for questions, but we can go a few more minutes with questions if folks have some questions you want to ask me at the end.
No, actually people are giving you lots of compliments. I don't see any open questions. You did a great job of pulling all that stuff together in the last 3 minutes. One thing, maybe you could show people the Learning Center real quick and where the tutorials are.
Sure.
Because I've met.
Under the help.
So I'm just going to mention that the Learning Center is built into Sketchpad. It's part of the software. It comes with it.
So the Learning Center has three parts. The welcome videos, which are very, very nice videos about using Sketchpad. Using Sketchpad, that section of the Learning Center has tutorials, a set of 12 tutorials that take you through all of the important construction ideas that Sketchpad makes possible in a very step-by-step way, supported by online videos. There's also a set of Sketchpad tips that come in both comic book and video format, and the reference center. The next, besides using Sketchpad, there is also the Teaching with Sketchpad portion of the Learning Center, which has some interviews with teachers describing how they use Sketchpad, videos of teachers actually using Sketchpad with their kids, and a whole set of sample activities from Sketchpad Lesson Link, more than 40 sample activities that you can use. So is that most of what you wanted me to show on the Learning Center?
That's great. Yeah, somebody asked earlier about iteration, and I was mentioning that one of the tutorials on the Pythagorean theorem shows, or fractals, and that tutorial shows how to do iteration, which leads then to fractals. But our time is up. I want to just mention again, those of you that came today, you'll be receiving an email that'll tell you how you can get the sketch that Scott used today, and we'll also be uploading the recording of this webinar, and those things should be dealt with in the next day or two. So you will receive all of the sketch and the worksheets in a zip file that were part of today's presentation by Scott. And Scott, I want to thank you.
Before everyone leaves, let me say one more thing, which is that we are involved in filling out the set of preliminary geometric function activities that I've created so far. We have plans for a number of additional activities that will fill in the holes, and for completing the activities with activity notes and so forth. And we are still looking for field testers who are eager to use these in a serious way with their students and give us feedback about how to improve and refine the activities that exist, as well as giving us suggestions about the sequence that we've put together so far and what else we ought to be doing to fill in that sequence. So anyone who is interested in that, I'd appreciate you emailing me. If I didn't leave my email address up here, I should have. It is stek@kcbtech.com.
All right, Scott. Well, thanks again for a great presentation. People have many positive things to say about it. And I want to thank all of you that came today, this evening, to join this webinar. Again, we'll be having technology, Common Core focused webinars every Tuesday at 7 o'clock Eastern Time, 4 o'clock Pacific Time. And yeah, thank you for spending your evening with us. And thanks, Scott, for doing such a great job of presenting such an interesting idea. And that'll be it for this webinar. When you leave, there's a brief survey. We would love it if you could fill out to give us feedback. And if you have any more questions, I'll leave the chat panel open for another couple of minutes. But at this point, the webinar is over. Thank you for coming.